Hello and welcome to a new video in my Spectrum Analyzer series. Now, it's been quite a while since I released a video in this series. In fact, I think it's been almost like a year or so. And quite a few people have asked whether the project was still alive, and I assure you that the project is still alive. I just didn't have much time to continue. But I'm determined to finish this, and I thank you for bearing with me. In that previous video, which I believe was number 9 in the series, I basically discussed what's inside this main chip. This is the DDS chip. It's an AD9850 DDS chip from Analog Devices. And I did so by discussing and building up internal building blocks of this and putting them together to hack up my own crude DDS. So if you're interested in that, I suggest you go and watch that. But I didn't discuss this chip in particular. Now, the way you use this chip inside is pretty much exactly what I discussed in that video. And to use that, you've got like this digital input here on the side. And in the end, what you have to do is you have to somehow load the frequency that you want to have at the output. In my case, I want to have 10.7 megahertz, but you load that frequency into the chip, and you can do that either in parallel or serially using these inputs here. And there is two special pins here. One is the word clock, and one is the frequency update. And basically, if you do it serially, you put one bit. I think it's at BD1, and you shift that in by pulsing the word clock, and then you go with the next bit and the next bit and the next bit and so on until you've got the whole word shifted in that you want to load into the chip. If you do it in parallel, you just put the whole byte here and you pulse the word clock. So in the end, loading something into this chip, it basically consists of setting the values properly and then pulsing the word clock, changing the values, pulsing the word clock again. We're going to look at that. But once you've got loaded everything into the chip, you have to pulse the frequency update pin here. And when you do that, then the DDS chip starts to output the frequency that you shifted in. So this is how it works, and you can see that the word clock and the frequency update pin, along with all the other pins here, are connected to this chip. The word clock and the frequency update, for example, are here. Now, what I want to focus at in this video is the stuff that's going on up here. Now, you can see two diodes, and again, the word clock net as well as the frequency update net are here. So basically, this is connected to here as well as to that node here, and the frequency update is connected to there as well as the frequency update there. So if you look at this, either you realize immediately what's going on here, or you might be a bit confused. Now, if you're confused, this video is for you, because this is essentially a discrete diode logic AND gate. And I want to look at that in a little bit more detail and discuss what you should use this for, what you can use this for, and what you shouldn't use this for. Okay, so let's look briefly at what logic gates are and what they're used for. Essentially, what you have is you have a mapping between some input logic states to an output logic state. For example, the OR gate maps two inputs A and B to an output Q in a particular way that is specified by this truth table. And if you look at this truth table, you see that the output is high, or 1, if at least one of the inputs is high. So the only case where it's actually not high is when both the inputs are low. You can extend this concept to more than 2 inputs. Now, similarly, the AND gate is a gate that has 2 inputs A and B, again an output Q, and the output Q is actually only high, or 1, when both inputs are high. In any other combination, the output is low. Now, That is very basic, and you probably know that, I guess. But the reason I'm discussing this is the first time I encountered these gates, I completely failed to understand what this was good for. Because usually what you get as an example is something like that. This is from let's say from a hypothetical alarm system. You've got two sensors, one is hooked to the window, so that sensor goes high when something is not in order with the windows, when somebody's trying to break in. And similarly, you have a noise sensor that is recording, when there is any noise inside the house. And when you arm the alarm, then you can have either the window sensor or the noise sensor or both go high, and together with the high of this alarm of this armed line here, the output will go high. So basically the output is low whenever armed is low. So that makes sense, because when you don't arm the alarm, it's not supposed to trigger, right? So but when you put armed to a logic high state, then the output gets high when the Windows sensor triggers or the noise sensor triggers or both triggers. So that is a typical example. However, in a way, this looks more like a high-level description of this alarm system than an actual circuit. And when I encountered this the first time, I looked at it, I was like, okay, yeah, but I mean, oh, fair enough, but that is not very interesting, is it? So that was my reaction. And what I didn't realize at the time, this was quite some time ago, but what I didn't realize is that you can use these concepts. The logic gates are essentially the fundamental building block of all digital electronics. You can use these to build memory, to build flip-flops, to build counters, to build 7-segment logic, to build multiplexers, essentially to build everything that is part of digital logic. And this is maybe a more interesting example here. Imagine that you have one of these 7-segment displays. You've got 7 segments plus a dot that I didn't put here, and depending on the number that you want to display on that 7-segment display, you have to turn on and off various of these segments in the display. And there are chips for that. Typically these have like 4 inputs, and you apply the number that you want to display in binary to these, and inside this chip there is some logic going on that makes the correct segments go on according to what you have on the input. Now, for example, if you think about this segment here, this segment should go on, I believe, this segment should go on when you want to display a 2, a 6, or an 8. But for any other number, it's supposed to be off. So somehow you have to map the binary number that you're applying here at the input to these outputs that are driving the 7-segment display. And you do this by hooking together a bunch of these logic gates here in a smart way. So by now you're probably quite bored, because up here I showed you something that you probably knew already. Then I cooked up a very abstract and strange application with this alarm thing here, and in the end I showed you another application that was basically available in a one-chip solution since years. So to make this interesting, I think next I will discuss actual circuits with diodes that are very simple and implement these gates here. Then we'll build them up and check their characteristics, and then go back to the main schematic to see how this is used there. Okay, so here are 2 gates, an OR gate on the left and an AND gate on the right, and these are both very, very simple circuits that you've probably seen before anyway. Now, these are also quite poor gates, and we'll see why this is when we play with them on the breadboard. But let's first try to understand how these work. Now, you have 2 inputs, A and B and the output Q here, you can see from this that this is passive, this is not powered. There is a ground connection here with a pull down 2 diodes, but there is no power. So basically, if we apply, I've got like this little sheet here to play with the inputs. If we ground both inputs, then both anodes are ground and both cathodes are pulled down to ground also, so the Q node is ground. Basically every single node in this circuit is ground in that case. And that makes sense, because if we consider ground to be logic low, then we've got 2 low inputs and a low output, which is in line with the OR truth table that I showed before. Now if I pull one of the 2 inputs high and keep the second one at ground potential, that could be 5 volts or whatever, it doesn't really matter that much, then the output should be logic high, right? Because OR says that at least one of the 2 inputs has to be high for the output to get high. And in fact, if we check out what's going on, we see that this high potential here generates a current flowing through that diode and then through the pull down here down to ground. If we have a low impedance load here, then there would also be some current flowing into whatever you hook up there at the next stage, or whatever load you have. So basically this means that the node Q, the output, is high because it's 1 diode drop below the input potential here, which can be considered high if the input voltage is sufficiently high. Note also that this diode here is in this case reverse biased, because we've got a high potential here and ground there on the anode. So there is no current flowing into whatever we have here at the input, but the diode is reverse biased. And because this is completely symmetric, we get exactly the same thing if we have the second input high and the first input low, just that this diode is reverse biased and this one is forward biased. And lastly, if we put both high, then if they're at exactly the same potential and the diodes are ideal, then well, both are forward biased, but in any case you're going to get a high potential here as well. If these are not ideal diodes, then probably one will have a slightly smaller drop than the other one and will reverse bias the other one. But in any case, what we get here is current flowing into this node here down to ground and into the output as before. So also in the case of 2 high inputs, we get a high output, which is exactly what we want. Now in the case of the AND gate, if we again ground both inputs, or let's look at the schematic first. We've got again 2 inputs here, 2 diodes that are now oriented differently, and also not a pull down, but we're pulling this node high to 5 volts or whatever supply we have. Let's just call it 5 volts for now. Now, if we ground both inputs, what we get is 2 diodes that are forward biased. So this point here, this node will get pulled anywhere close to ground because this diode is forward biased, this diode is forward biased. So there is current flowing through this resistor here and into either or both of the diodes. The point here is that the potential at this node is going to be quite low. In fact, it's going to be 1 diode drop above ground. So in that case, the output can be considered low because it's close to ground. Now, since this is an AND gate, pulling up one of the 2 inputs to logic high shouldn't change anything with the output. And in fact, I did exactly that here. One input here now is logic high, 5 volts, and the other one is still grounded. And in fact, now this diode here is reverse biased. This one, the cathode sits at 5 volts, while the anode is anywhere at or below 5 volts. So this diode is reverse biased, but this diode is still forward biased. So there is current flowing through the resistor, through that diode down to ground. And that node is then still 1 diode drop above ground and is still at logic low potential. So with 1 input high, only 1 input high out of 2, we still get an output of logic low. which is exactly what we want in the case of the AND gate. Now I'm not going to discuss like swapping these two with the other input high, because it's exactly the same symmetric case as before. But if I pull both high, now that is interesting case, because now this diode here is reverse biased, cathode at 5 volts, anode somewhere at or below 5 volts, and the same for this diode, since this is completely the same. So since these diodes here are reverse biased, this node now sits at 5 volts, assuming a high impedance load here. And that's exactly what we want again, because that is the only case out of 4 where the output Q gets high, and that is in line with the truth table of an AND gate. So let's build up this AND gate on a breadboard. The OR gate is going to be quite similar, but let's build up the AND gate and see what kind of properties this circuit has in practice. Okay, so I built up the circuit on the breadboard. This is where I apply power, and it's actually already powered, so I should be able to measure close to 5 volts here. That's my supply voltage, 5 volts. The resistor here is a 1K resistor, corresponding to that pull-up resistor there, and I put the blue LED as a load here from the output down to ground. We're going to discuss whether I need a current limiting resistor or not for that blue LED. The two diodes are here across the breadboards. These are 1N4148 small signal diodes, I guess, and the wiring is just there for me to be able to set the input voltage on either input. Now the blue wires are connected, which means that the both inputs are connected to ground, and the LED is off, which makes sense because in the AND gate we actually need both inputs to be high for the output to go high, and now when both are low, then the output is supposed to be low, which is the case. So this seems to be fine. However, let's measure the actual output voltage that we have here. It should be 0 volts, right? But the output actually sits at somewhere between 0.6 and 0.7 volts, which is no surprise, because that is the forward voltage of these diodes that are forward biased. So right now we have current flowing through this resistor here, through the diodes down to ground, because the two inputs are connected to ground. And that's already a little bit of a problem, because remember how I discussed before that we might want to chain these. So if this output is 0.7 volts and is an input to, let's say, another one of these circuits, if we chain these, then the input that's supposed to be at ground is actually 0.7 volts, and we have yet another 0.7 volts of drop here. So the next output is going to be already at 1.4 volts, and this is going to stack up very quickly. That is one of the problems we have with these kinds of circuits. We might, if you think you can get around this with putting a series diode here, then you're probably mistaken, because while that would actually or might reduce the voltage at the output, it will also reduce the voltage when we have an output of logic high, which would have exactly the same effect. So we don't want that to happen. And in addition to that, the circuit wouldn't actually be able to sink any current. So really that's a bit of a limitation there. Now what I will do is I will disconnect output B from ground, or input B rather I should say, and set this to high. Now nothing should change because the other diode is still forward biased. Well, we can actually measure this, just for the sake of completeness. Now this diode here is forward biased because it's got 0.6 volts at the anode, 0.5 volts, not 0.5 volts, 5 volts at the cathode, but the top diode is still forward biased. The anode sits at 0.6 volts and the cathode actually sits at ground. So what we have is exactly the same we had before. It's just that the current is just flowing through one diode instead of two. But the LED is still off, the output is still low, or 0.7 volts. And that's exactly what we should get, because the output is only supposed to get high when both inputs are connected to logic high. So let's do that. Let me unplug the input A, which is the one that was still grounded. And actually, while I do that, you'll observe that the LED goes on. Which is a prime example why you should never leave inputs floating, because right now the voltage at input A is the logic state is undefined, and that's bad, because in that case anything can happen, and you know, maybe this LED going on is what you want, but maybe not. So leaving input floating is generally not a good idea. Now if I connect input A now to logic high, we've got now both diodes reverse biased, which is why the current cannot flow through the resistor into the diode and has to go into the load, which is the LED. Now let's measure the output voltage, because if this were, you know, an ideal gate, we would have 5 volts there. So let's have a look at what we get there. And we don't have 5 volts. Well, okay, something is intermittent here. But the voltage is not 5 volts, it's 2.7 volts, which is not a surprise, because that's the diode drop of the blue LED. So the LED is loading down the output by quite a bit. Really, this is no surprise, because this resistor acts as a dropper resistor, so it's limiting the current and dropping the voltage at that node to whatever the forward voltage of the blue LED is. So again, this is not exactly what we want, because if we were to change two of these guys here and we were not to apply 5 volts but 2.7 volts at the input, things wouldn't go exactly the way we want. So this is lacking all the characteristics that we'd like to have from nice logic gates, you know, low output impedance, because if the output is high, the output impedance is actually this resistor value here, because the current has to flow through this resistor. So you might think that you could reduce this resistor in order to reduce the output impedance, which is true, but if the output is low, then the current flows through that resistor into the diode, and that current is basically wasted. So that's not exactly a great approach either. So if the output is high, the output impedance is that resistor value here. If the output is low, it's even worse, because then the output impedance is actually the output impedance of whatever we hook here to the input. So we don't have something that has a low output impedance and a high input impedance. And really, this is why for logic gates, in the way I discussed them before, you know, for actually building all these digital circuits, it's really not a good way to go, especially if you're not buffering this. But this has its place. The reason I'm actually doing this video is that many people know about this. You know, this is not exactly rocket science. It's probably the first thing you see when you're talking about digital circuits, is how to build these discrete gates. But while quite a few people are aware of that, often they kind of tend to forget about this. And in the circuit of that DDS module, there is a nice application to this, and this is what I want to discuss next. Okay, so we're back to the schematic of the DDS module. That is the diode circuit that I showed in the very beginning, and maybe after what I just discussed, this makes more sense now. And that is a page of the datasheet of the DDS chip of this AD9850 from Analog Devices. And this shows how you're supposed to clock in the target frequency. Basically, you clock in the bits. This is shown here below in that table. So W0 is the least significant bit of the target frequency, and W1 is the next significant bit, and so on. And you're clocking these in by pulsing the W clock input. You clock them in bit by bit, and then when you're done, you can then clock the frequency update, or wiggle the frequency update pin, and that will then cause the target frequency to change to whatever you just clocked in. If you look at this, you'll notice that actually W clock and frequency update, apart from here, but you don't have to do this, simultaneously, they're never high at the same time, because you're first clocking in all the data, and when you're done with that, then you pulse the frequency update. And the guy who did this, Scotty, of course noticed that, and there is a bit of a shortage of input pins here. Now, while I believe that strictly it is not necessary to be able to reset that chip, it's still something that is very nice to have. And he decided to hook this gate here to the reset pin, which is active high. So the way this works normally is you're clocking in the data with W clock. When you're done, you wiggle frequency update, and because these are connected here, they will then update the chip to output that 10.7 megahertz signal. Now, if the two inputs, W clock and frequency update, remember that these are also connected here, that's just like a local name, because these are never high at the same time. This means that always one of these two diodes here is forward biased, which also means that the node here, which is actually connected to the reset pin, is always pulled towards ground. So during normal operation, let's say, a reset never happens, because always either W clock or frequency update or both are low. Now, if you want to force a reset, you can on purpose set W clock and frequency update simultaneously to a high logic level. And once you do that, then both diodes are reverse biased, and there is no current flowing through the resistor down to ground, because when these are set input low, then they're basically connected to ground. But if you put them too high, then you reverse these diodes, and that is not happening. And as a consequence, the node here is pulled to the supply voltage, and the chip resets. So basically, this is a nice way to spare a pin and to figure out, with a combination of inputs or input values that are never happening during normal operation, to be able to reset that chip. Lastly, notice that these are Schottky diodes, and that is not a coincidence, because remember that one of the problems we had was that actually, if you forward bias both, or actually only one of the two diodes, the node here is not ground, but it's actually corresponding to the diode drop across the diode. And as I said, if the diode drop is sufficiently high, then the chip might not recognize this to be logic low, and putting a Schottky diode here with an inherently low voltage drop, 0.3, 0.4, might be even, it really depends on the Schottky diode, but it's typically considerably lower compared to a standard silicon diode. You can get away with that, because then, and we're going to measure this once I build it up, just because I'm curious, but it's going to be much lower than 0.7 volts, which is good, because we want to be sure that the chip recognizes this as logic low and doesn't reset when it's not supposed. Okay, thank you very much for watching. I hope that was interesting. There's a few more things in this schematic that I want to discuss, and once I've done that, I want to build it up and see how it performs. If you have any comments or things to share, please do so down in the comments, and I hope to see you for the next one.